Okay, that should be willing to cooperate now. Let's take a look. Okay, I think we're all set. Let me know if you're in Zoom and the audio is not coming through, but I think we should be all set. Well, welcome back, everyone. I don't have a huge list of announcements, and they do get deleted once I have to unshare the screen and reshare it with all these weird bugs in Zoom, but here's pretty much our strategy. Just take a quick screenshot and pretend that was the real thing right there. So there's our announcements. We have our quiz that's due today, but that's pretty much going to be the pattern for the rest of the semester. I'll keep on putting up down those notations just as reminders. But for the moment, this is where we're at in the course. We're in section 5.6. And this is a good place to be since we're almost done with chapter 5. Chapter 6 is going to be the last set of topics in the entire semester for this class. We'll be dealing with exponential functions and logarithms, and then that'll be really great preparation for anything you might do with that kind of work, going into calculus or doing some engineering and so on. So that's where we're at so far. And for the other announcements I didn't have on this page, we also had our exam return. So our average grade on the second exam came out to 81%. Let's compare that with exam 1. That's always kind of fun. On exam 1, it was 85.9%. So it looks like it was a tougher exam, that's for sure, going by averages. And on the second exam, the maximum grade was 100%. So congratulations to that person. That takes a lot of practice to get there. These are really tricky exams with lots of small nuanced details. And just like before, I have the solutions posted. So if you have any questions on these problems, you could take a look at this document or come directly to me. I'd be very happy to help out. And this is a good time to open up to the class. Any questions that folks would like to discuss at the moment on the exam? Okay, maybe one last reminder. This is always kind of confusing. You always get 2 scores. Your first score right here is a fraction out of the total points, 85. And it does get converted into a percentage on the actual Moodle website once I upload it. So you'll see exam 2 as a percentage here. And your course score was just your overall grade at the moment of completing grading the exams. I believe I finished them on Friday. So after pulling in your quiz grades, the ALEKS homework, and the average of your 2 exams, that brings you to your course grade right here. Well, any questions about that, folks, before we jump back into the notes? Okay, well, here we are. That's the wrong one. Let me get the right set of notes. We're not quite there yet. That's like time traveling. We're in section 5.6. 5.7 is a pretty short section, but this one is not. There's a lot of tiny little details we have to get through on this, but our goal is to go through it very methodically, very slowly, so they'll prepare you for the ALEKS problems. Any quiz problem that we have on this document will probably be our 10th quiz based off these notes here. And let's start off with just the good old definition. If we're talking about a polynomial function, then we have to talk about what the degree might be. The degree n comes from the leading term here, where the highest power of x appears. And this is just the general way to write a polynomial. It's kind of annoying because it looks more abstract than it really is once we take a look at that line right there. But a typical example for a polynomial could just be, say, f of x equals 3x minus 4, for an example. So polynomials could be constants. They could be linear functions like this one, which would be degree 1, or quadratics, or a general polynomial like this here. But once we take a polynomial and divide it by a second polynomial, now we're dealing with a rational function. So we have one polynomial up above, one polynomial down below here to form that entire rational function. And now that looks just really, really bad because that's the general form of this thing. But here are some examples of a typical rational function. The rational function could be, say, f of x equals, let's just take this polynomial here because we can. It could be any polynomial, 3x minus 4. And it could be divided by some other polynomial, maybe 17x squared plus 6. So that'd be a typical example of a rational function. Just has to have some polynomial of any degree in the numerator, and same for the denominator with no zeros in our denominator. So for just a couple more quick examples, another one could be like this. F of x equals 7 over x plus 3. This one looks odd because the denominator is of degree 1, but the numerator is just a constant. That is allowed. That's a degree 0 polynomial. And so you can have a constant in numerator or denominator, or even both. Another example, let's change the names on these. I want this one to be g of x. Let's let this one be h of x. This one would also be considered a rational function. Just the number 7, all on its own, is rational in a really strange way. It's not really rational in the sense that you have things that vary in numerator and denominator. But if you really wanted to, you could call this 7 over 1. So now it's a degree 0 polynomial in the numerator, degree 0 polynomial in the denominator. And again, strange function, but the takeaway is an ordinary integer would be considered rational through this definition here. But these ones like the g function or the f function are more typical. We'll usually see a variable in either the numerator or denominator, most likely both. Well, any questions so far, folks, about these typical examples of rational functions? Okay, one thing that we'll need quite a lot is the degrees of these things. We're not trying to look at the degree of the function overall like we did for polynomials, but we would like to know the degree of the numerator versus the degree of the denominator whenever we write one down. So if we focus on just the first function, f of x, we'll say that up here, this is of degree 1, because 1 is the highest power that emerges in the numerator, and the denominator will be of degree 2, only because of that 2 right there being the highest power for denominator. So we want to pay special attentions to both the degrees of these things. And looking at our function, the degree of p of x, that's the thing going in the numerator, that one is degree n, only because of that term there. The degree of q of x, that comes from this function, q of x in the denominator. It's indicated it's degree m, and that's only because m is the highest power that emerges down below. So that's the business with these rational functions. Essentially, what we're going to do with these things is we're going to look at how to graph them. We need information about asymptotes, well, vertical, horizontal, we need x-intercepts, y-intercepts, and a couple more tricks. Then after that, we'll look at a couple of inequalities, and we'll be on our way to section 5.7. This one's a little bit longer, so it's probably going to spill over to Thursday's class. Well, let's take a look right away at example 1. It says for the rational function given below, we want to find the domain in interval notation. Then we'll find the x and the y-intercepts. Let's begin with domain on this thing. For this kind of function, really all we need to worry about is what happens in the denominator. Honestly, this section's kind of nice because we did these kinds of problems all the way back in chapter 3 when we were doing domains of these kinds of functions. So here's the strategy. Only because we have a fraction, we're going to set 2x squared minus 7x minus 15 equal to 0. What we're looking for are values excluded from the domain, values x could never take, because they would result of 0 in the denominator, causing division by 0. But now to solve this equation, our go-to method is to try to factor it. Let's split this up as a pair of binomials multiplying together. We can split 2x squared as a 2x times x. A negative here is going to reduce the trial and error massively. Our signs have to be mixed now. So it's going to be plus or minus. I might have them backwards, but I'm going to leave them like here for the moment and fix them if necessary. Next thing we do is factor 15, and 3 and 5 is usually a good call on this. I'll put the 5 here. The only reason I put the 5 here is I'm anticipating that multiplication. That's going to give us a negative 10x. And that's already really, really close to negative 7x that we're gunning for on this. So the other factor we can throw here, 3, multiply here to here, that's plus 3x, resulting into a negative 7x, which was our target. That tells us we have the right factorization, and we can go to the next step now. Any questions, folks, on getting it factored? Okay, next step on this equation solving here is, because of the factorization set to 0, this immediately implies either 2x plus 3 is 0, or x minus 5 equals 0. These can both essentially be solved in one step. On the first one, subtract 3, divide by 2, and we get negative 3/2. And on this one, just add 5 to both sides, and we'll get a positive 5. So we solved the equation where we set the denominator equal to 0. Right here, we can just write out the domain immediately. But let's emphasize that what we found would be the so-called excluded values. The word excluded values makes sense in a certain sense because we're saying those two numbers are excluded from the domain. We're going to write a domain and having all real numbers except those two values right there. Those are the only two ways you could potentially divide by 0. So our domain is finally equal to, we'll take this negative infinity up to that negative number. So parenthesis, negative infinity to negative 3/2. Now we have to make a judgment call, right? Is this a bracket or is this a parenthesis at the end? Exactly. If we put in a bracket, we're saying negative 3/2 works, but it absolutely doesn't. It causes division by 0 right away. So as everyone said, the parenthesis is the right thing. We're throwing away that domain element. Everything up to that value is in the domain. But then you can go to the right of that value, go from negative 3/2 all the way to that problem point at 5. And I'm noticing I need just a quick border right here. Union, one last one, go from 5 to infinity. And that's the whole domain on this thing. So who knows what's happening at negative 3/2 or 5, but those are humongous problem points of the function. They're not even in the domain of that thing. Sometimes people use fancy words like the function blows up at 5 or negative 3/2 because we're looking at what's going to eventually be a vertical asymptote when we consider those graphs. So those are some massive problem points. We take them out, and that's finally our domain. Any questions or comments at the moment, folks? Okay, next thing we want are x and y intercepts. Saving that for last, since this step right here always kind of goes the same way. Let's write this out carefully. The process will be, once we get some more space, let's make this a whole new page. Things always look like they'll fit at home, but then on this resolution, it gets a little bit bigger writing things down. So let's organize and say over here, we're solving for our x-intercepts. I'm going to put my answers to the right of this column, but then I'm going to put the work right down below it to show the process. To get an x-intercept, all we do is we take the original function and set it equal to 0. Now there's a huge shortcut to this. Turns out the answer is just 7 and there's nothing more to do. But let me show the process of how this really goes. Because we're setting something to 0, the denominator has absolutely no influence on this problem. In fact, let's write this in orange just to emphasize this really is an optional step. F of x equals 0 can now be thought of as x minus 7. Let me fix that right there. Divide by 2x squared minus 7x minus 15 equals 0. But your immediate first step is multiply both sides of the equation by that denominator. The effect is you're just taking that denominator, feeding it to the right-hand side where it's multiplied by 0, and you automatically get this. X minus 7 equals 0, which is an equation we can solve in one step. But let's write down the idea with this one. If you're finding x-intercepts and you're dealing with something that's a fraction, a rational function, only the numerator matters when you set this equal to 0. There's nothing that can happen in the denominator that could cause this to be equal to 0 whatsoever. That's really kind of strange. So I'll put here as the note. To find x-intercepts, set the numerator, the top of the function or the fraction. Our numerator was x minus 7 equal to 0. So every time you see a rational function, that's pretty much all you have to do. And that means for a lot of these, you can just eyeball it. Put in a 7 and you will have a 0 in the numerator. You will not get 0 below because those are the only ways to get 0 below, those two numbers. So automatically the whole thing is just 0 when you pick 7. So x is 7, that's our x-intercept. I'll put my official answer as an ordered pair and write 7, 0. But I'll take these either way. If you give me 7, 0, I'm totally fine with that. Sometimes that's what Alex wants. If you just say x equals 7, that's okay too, since sometimes that's what Alex wants as well. It's hard to tell what they're gunning for. So that's a process with x-intercepts. And it turns out y-intercepts even faster for this kind of work. So let's write it down here. To get a y-intercept, let me start boxing these answers because this is a lot of work all of a sudden. So I have a domain, I have a x-intercept right here. And I'll box the y-intercept once we find it. So now for y-intercept, here's the strategy each and every time. For y-intercept, you're always setting your first coordinate equal to 0. Much like an x-intercept, your second coordinate's what's 0. But if you set x to 0, you just come right up over here, calculate f of x. Well, now that's f of 0 for x. We'll plug 0 in the numerator and denominator. Up above, it's just a negative 7. Down below, it's a negative 15. And so we get a positive 7/15 when we do that work. So the official answer, I'll think of it as an ordered pair. I would accept both an ordered pair or just y equals 7/15. So there it is. There's our x-intercept, there's our y-intercept, and a problematic domain, but nothing we can do about that for this function. That's all we were meant to do here, but if we did want to plot this function, this is a pretty good head start already. Well, any questions, folks, before we maybe take a break on this one and take a look at the graph? Okay, let's see what the graph looks like and see if we can make sense of this information, particularly the domain, when we compare it against its graph. Our goal is to show how to do these by hand, but it's a lot of extra steps and strange steps compared to what we've seen before. So this will be our freebie. Let's just plot this and see how it goes. F of x equals x minus 7 in the numerator. Down below, it's 2x squared minus 7x minus 15. And here's what the function looks like as its official graph. Kind of a wild looking function, but we did find a y-intercept right here. It's in fraction form, 0.467 rather. X-intercepts, we said it was at 7, 0. That looks about right. But there's also weird stuff happening on this graph. Let's see if we can make this slightly, no, it might look just as well as a smaller picture. Let's maybe put it right here. And I'd say the biggest takeaway with doing this kind of work is what was happening with the domain, and as well what was happening with those excluded values. They become x-intercepts, and the function right at those values, again, it definitely behaves pretty wildly, right? Right here, it does pass a vertical line test, but it's increasing so rapidly because once we lost that domain element right at x equals 5, we obtain what we'll call a vertical asymptote right at this location. We could say it here and now. This is a vertical asymptote. Always thought that word was weird, but all we mean is a barrier that the function gets closer and closer to the closer the x value gets to 5. Here it's blowing up, going towards positive infinity. We come in from the right-hand side and let our numbers get smaller, approaching 5. This one is also blowing up. It's becoming large negative, heading down to negative infinity. And this one at negative 3/2, it's right here as an asymptote. If I can kind of get it down there, negative 3/2 should be about negative 1.5. I think I kind of missed. Let me try it a little bit harder. Here's negative 1, here's negative 2. So right here is the other asymptote. X equals negative 3/2. So once we set the denominator equal to 0 and solve that thing, we did it right up over here. We found two things at once. We found the domain, and we also found the vertical asymptotes on the graph. We need more information to produce graphs in a nice, reliable way and an efficient way, but this is a good start, knowing where your vertical asymptotes are. One nice thing about a vertical asymptote is the graph of a function. Now, this one is absolute. It never crosses a vertical asymptote. But when it comes to horizontal asymptotes, we're going to take a look at next. Those it can cross. In fact, it could cross it multiple times. Just in the long run, it eventually gets closer and closer to a horizontal asymptote. In a certain sense, vertical asymptotes are nice. They're literal barriers on your graph that your function could never actually cross, like on this one here. Horizontal asymptotes, a little bit trickier. It can cross those. Well, any questions, folks, with the algebra here or the graph down below? Okay, well, our goal here is to try to produce some of these freehand sketch graphs. We're not going to try to plot them perfectly. It's going to be the same in spirit like we did with the polynomial functions. We'll look for the right information, we'll get asymptotes down, and then just start plotting them like we see about like this. First thing we need, though, is information about horizontal asymptotes. Here, just for completeness, a vertical asymptote is defined right here as a vertical line, x equals a. We wrote these as x equals 5, x equals negative 3/2, where the graph tends towards the positive or negative infinity as the inputs approach a. This one's heading towards positive infinity on this branch, heading towards negative infinity on that branch. But now horizontal asymptotes are kind of a different deal. It says here, a horizontal asymptote of our graph is a horizontal line. So we'd be writing them like this, a y equals b, rather than an x equals some value, like negative 3/2. The graph will approach this line as the inputs increase or decrease without bound. In other words, your horizontal asymptote only really takes effect if you're a very large negative, say far to the right this way, or very large positive going off in that direction. So let's take a look at what could happen. This becomes a pretty much an awesome cheat sheet for us. Any kind of rational function we're given, we can determine what the horizontal asymptote is, sometimes just by taking a look at it. Sometimes we'll say there are no asymptotes just by considering the degrees in numerator and denominator. And I would say that this page right here, let's make this really apparent if you come back to the notes. This is an extremely important theorem. Theorem just means a mathematical fact that we could prove rigorously from scratch. And the analogy with this one is, if we go back to section 5.3, or excuse me, 5.2, that theorem we're taking a look at is much like this one, the end behavior. This just gets used all of the time when we're trying to plot the functions. So it double dips all over the course in different locations. And that's kind of what's going to happen with this right here. It plays the same kind of role. It tells us exactly what should happen with any rational function. So this would be something I'd print out, have it available if I'm solving a quiz, doing it an Alex problem. Yeah, go ahead. It's not, because the trouble with that is, I'm glad you asked about that there. We're required to have a literal polynomial in the numerator, a literal polynomial in the denominator, but then that means n has to be an integer at every time. So if you write a function that goes like this, you said square root in the denominator.
Well, no, the square root of that.
Actually, root x wouldn't have a horizontal asymptote. It kind of looks like it does, because if you put it on the graph, y equals square root x, it looks like it's settling down, right? It looks like it levels off, but here's the trouble with this function. Let me call it f of x. And then down below, if it had a horizontal asymptote, I would be settling down on this number here. If I put in a larger number, it shouldn't increase too much. In fact, it's got to be getting close to something. But if I put in squared, I have power 10. Cubed, I'm at 31. Power 4, I'm at 100. I can make this as big as I want just by putting a high enough power. But if I have a function that goes like this, 1 over, let's just say, x, this one does have a horizontal asymptote. The horizontal asymptote would be the line y equals 0. But if I make x bigger and bigger on this one, well, it's just going to get smaller and smaller in the output. We're at 0.000001 when we're at 10 to the power 6. Put in 10 to the power 7, and it's even smaller. Desmos is now using scientific notation to describe just how small it goes. So this is one that would have a horizontal asymptote. And honestly, that's why this is kind of tricky. This one right here is not a rational function. And if we don't have a rational function, wild things can happen with our horizontal asymptotes. But if we insist we're only dealing with these things, where the powers of x are ordinary positive integers like power 3, power 5, no power 1/2 like the root x, then this theorem describes the only possibilities ever for your horizontal asymptotes. It's a trichotomy. Only 3 different things could ever happen here. But other questions so far? Okay, I thought for these, I put down 3 really fast examples. And all I wanted to do on these examples was say what the horizontal asymptote would be, so we could see what happens when we track through this theorem. It's all about the degrees of your p of x, that's what's in the numerator, your q of x, that goes in the denominator here. So every time we analyze these things, first thing I would say right away is, what's the degree of the numerator? Anyone spot the degree of the top function there? Exactly, we'd have degree 2. The denominator's degree comes from that term. These are not always given to be in standard form where it has, say, the highest power term, the next highest, and so on. This one has the constant, and then the highest term is right here. So we have to definitely keep our eyes open for that. I put that in some of my problems here because it's also in the ALEKS system as well. This one is of degree 1. And so it turns out the degree of p of x is greater than the degree of q of x. And each and every time this happens, there will be no horizontal asymptote whatsoever on this graph, much like, say, the square root example we were taking a look at. So let's put here as our conclusion. Only because of the degree 2 here being the winner, there is no horizontal asymptote. So what happens on this function? There is actually an asymptote on it, but it's just not horizontal. We'll see how to find it towards the end of the notes. Let's take a peek at what this function does. Let me import it. It's f of x is equal to 4x squared plus 4 division by 3 minus 5x. So that's what this function does. It's pretty wild. It's blowing up, but moving kind of like a line, a linear function when we go to the left. If you go to the right, there's also what looks like a line going down in that way. We're going to later call this one a slant asymptote, but this one definitely has no horizontal asymptote whatsoever. Any questions about that first example here? Okay, so at the moment, it's really a game about degrees. The numerator wins, you'll never have a horizontal asymptote. So let's change to case number 2. This time, the degree of P of X is going to be equal to the degree of the denominator Q of X. So case 2 is when we have a tie, whereas case 1, this is when the numerator wins. But here we have a tie. It's a tie in the sense that from this right here, we can say the degree equals 2 for the numerator. From this term right here, we can say the degree is 2 for the denominator. So here's our equality, our two-way tie. We have equal degrees, numerator and denominator. In this case, there will be a horizontal asymptote, and its computation is extremely fast. Let's take a look at the notes. It says the horizontal asymptote is y equals k, where k is the ratio of the leading coefficient of P of X to the leading coefficient of Q of X. That's not my favorite way to verbalize that. Here's how I would actually write this down based off that sentence. Let me try again. We're going to need a pen. Y equals, it's a ratio, so we're forming a fraction. When it said the ratio of leading coefficient of P of X, we're talking about the 4 right there. That goes to the numerator, the way they wrote this out. To the leading coefficient of Q of X, go to our Q of X, we grab that coefficient and put it down right here. Coefficient down below is tricky because we also have to grab the sign of -5. So this is altogether y equals -4/5. That means this should be settling down on, this is altogether -0.8 as a horizontal asymptote. So let's take a look at the graph and see if that's really happening on this one, just to get a feel for it. So all I've done in this function is I bumped up the degree in the denominator. It's practically the same function as the one right above. So I'm going to put it power 2 right in this location. At power 2, this is how the graph changes. It changes a lot with one little adjustment of the exponent. Now let's put a second graph for the horizontal line. Y equals -4/5. And double equality is not going to work here. There we go. That looks like a horizontal asymptote, and that's what they ought to do. Right around here, well, the curve is nowhere next to the black line of the horizontal asymptote. But as the value of x gets large negative, if it heads off to this direction, it's heading off to the value of about -0.8 and some change. It's heading off to -0.8, really. If we zoomed out even more, we'd be getting closer and closer to a -0.8. Here I have a -0.805, for example. So yeah, absolutely. If we have a tie in the degree, there will absolutely be, oh, I'm on the wrong one. For a tie, we get a horizontal asymptote, and it's just picking off coefficients. That allows us to even find the equation for it instantly. But it means it's a lot of things that we have to visually inspect to be very careful with. And that's why, again, I would call this an extremely important theorem. This is a good one to print off, I'd say, and just have ready to go whenever you're doing these kinds of problems, because its importance is, again, at the same level as this one was right here. Well, let's try out the third case. So numerator 1, in this case 1, in case 2, there's a tie, but in case 3, now the denominator wins. It says if the degree of P of X is less than the degree of Q of X, your horizontal asymptote is y equals 0. I mean, that's even better because it's telling you no matter what, that will be your asymptote. Let's put here just to make the notes look somewhat organized. Denominator wins. I don't know why that feels like exclamation marks are appropriate there. The reason the denominator won is because in the numerator, up above, this is now degree 1, but down below, it's still of degree 2. So once we see this right here, the degree of the denominator is higher, the immediate and foregone conclusion is that y equals 0 is the horizontal asymptote. But let's check that out. One last graph, folks. Just about the same function. I have 3 minus 5x squared still in the denominator. My only change is I'm bumping down the power right here. So we're going to take a 4x squared and just make it be an x. Now, what happened to that? Let's take a look. Let's maybe turn off that right there. Here's our new graph. And yeah, a horizontal asymptote of y equals 0. Really hard to plot because it overrides right on the x-axis. Y equals 0 is the x-axis. But as long as we're very far to the left or very far to the right, those function values, the second coordinate here on the point, is certainly getting closer and closer to 0. You can make this as close as you want to 0 by making the value of f as large possible, positive or negative. Let's check that out. If we put in f of 1, we're at -4. At 10, now it's 0.8 negative. Square that and we have a couple extra zeros. Let's do something wild. Let's just put, say, into 1,000. It says it's undefined. That's actually a lie. It's just we left the realm of the size of integers that Desmos even wants to deal with. But 10 to the power of 100, we have -8 to 10 to the power -101. That's effectively 0 for anything that would be applied. So that's our big theorem that's going to control how we plot a lot of these functions. Vertical asymptotes aren't so bad. We just set the denominator to 0 and solve. But horizontal asymptotes always runs through this theorem right here as a start. So this will be a note that I will often call up just to help us out when we're doing these problems. Any other questions or comments, folks, before we try the next example? Okay, with where we are so far in the notes, example 2 is going to be kind of the big one. The goal here is to plot various rational functions like you'll see in the homework. So there's one where it's degree 0 in the numerator. Numerator here has degree 2. And this one, we'll just figure out what happens to this. After that, we'll do something that looks nasty. This one is Alex inspired, you can almost tell. This will be the one where I feel like this is the worst problem in Alex. We'll show how that goes. And then finally, we will take a look at how to calculate a slant asymptote. This definition is wild because I also put an example inside. I feel like this is a tricky topic. So we'll take a look at that as we solve. And then last concepts will be inequalities and an Alex calculator problem. Well, let's start off and begin with just ordinary plotting of these functions. Any questions or comments, folks, before we give this a start? Okay. So once again, our goal is to not try to get the most perfect plot whatsoever, but we want a qualitative plot that captures most of the important information that we would care about when we're dealing with a rational function. So it says here, find XY intercepts, the equations of all asymptotes, then sketch the graph. I'm going to often use this as a shorthand. For vertical asymptote, I'll write this as V for vertical, ASY for asymptote. That's just a good shorthand for notes regardless. And likewise for horizontal asymptote, I'll use this shorthand, H for horizontal, ASY for asymptote. So if you're wondering what that means in the notes, it'll be defined right here officially. And I think the good place to start on this is X and Y intercepts. Well, they asked for us first, but the thing that's really new about these problems are asymptotes. So let's begin with dealing with that. Anyone see what the horizontal asymptote, for example, ought to be here? Yeah, absolutely. I'd say a good call when you do these kinds of problems is look at the degrees. There's no X, that's degree 0 up above. Down below, there is an X, its highest power is 1. So degree 1, and we can say denominator wins. Wins in the sense of it's of higher degree. And then just like you said, horizontal asymptote is this equation, y equals 0. Only because of that information right there. Does that make sense to folks on getting that asymptote? Awesome. It's really pretty fast, but it's definitely tricky. If you have this at your ready, then that's a good way to think about this one. Let's try this again. We also want to find the vertical asymptote. For that, I'm going to state the answer right here and put the work down below. Unless anyone sees it instantly. Anyone happen to spot what the vertical asymptote must be? The good news with this is it's really kind of a redo of domain. If you think of how would I find the domain of that function, you're doing the same motions of how would I find the vertical asymptote of that function. Either way, to get domain, say, you would take 18x minus 2 and set that thing to 0. That would be a domain issue since we can't divide by 0. Next, solve for x. We'll have 18x equals 2. X equals 2/18. So x equals 1/9. And that's it, folks. That's our vertical asymptotes right there. So I'll put here x equals 1/9. I mean, it's kind of redundant, right? I didn't really change it when I brought it up above. But either way, here's our here's our vertical asymptote. And here's our horizontal one. We still need some x and y intercepts, and we still might have to evaluate the function at a couple points just to tell where the curve even is. But right now, this is not a bad time to just start plotting this whole thing. Once you start getting information coming in, particularly asymptotes, we'll start sketching them using dashed lines as indicated right here. So our plot does need to have asymptotes to be considered fully correct for credit, but putting down y equals 0, if you skipped that one, I would have been okay with that. Let me actually change the color on this one. I'll plot the asymptotes in purple, so we'll tell which ones we're plotting. But if you really want to get that asymptote on your paper, here's the way you could plot it. I'll show it like this. Y equals 0 goes through the x-axis. So here it is, y equals 0. I wouldn't mind if you decide not to plot that one. I think it's a good idea because it's a reminder our curve has to approach the x-axis on this end to the right and on this end to the far left. Now let's go over, plot our vertical asymptote. This is 1/9, so it's practically the the y-axis here. I'll set this at 1. Let me make that look like it's part of the graph, really. I'll set the scale by putting a 1 there. At 1/9, I'll just try to do my best to plot it really, really close to the y-axis. So here is x equals positive 1/9. So asymptotes are now on the plot, and we can proceed down to the next steps. Any questions at all, folks, with getting those put down? Okay, let's go over next to, we want x and y intercepts. That always goes the same kind of way. Let me copy this in case we have to scroll up and down a little bit. I didn't quite copy that completely. There's supposed to be an F there. Okay, now it looks a little bit more official. Oh, geez. Sorry, some struggles with technology here. Now let's try some x-intercepts maybe. For the x-intercept, we always take the numerator, set it equal to, and solve. But what does that mean about x-intercepts on this one if we tried that? It would be really weird, right? We'd be taking -9, setting it equal to 0. Exactly. So if you're missing a variable in the numerator of your function, you can say just immediately for x-intercepts, none. It's kind of nice, and that's only because this has no solution. Now, what that tells us about the plot is when we go to sketch the plot, we can never do anything like this for an example. That would imply there's an x-intercept right here, but we just said there are none. We cannot even touch the x-axis when we go to put the final plot on this thing. So that's definitely good information for us. Now let's do y-intercept. So for the y-intercept, this one's even fast, well, about as fast, I'd say. You're plugging in 0 for x for a y-intercept. I'll leave this as with a question mark until we find that value. That means all you're doing is calculating f of 0. That 0 goes right here, which means it goes right in that location, the function, and we'll get -9 divided by -2, giving us a 9/2 altogether, or 4.5 if you prefer. So now we have a y-intercept. And hey, that means we can plot that thing. If that's the scale at 1 right here, then if we decide to keep the same scale, that'll be 1, 2, 3. Oh dear, let's keep on going. 4, 5, and 4.5 would be way up here. So we have at least one point determined on this graph. We have a vertical asymptote we'll never cross, and a horizontal asymptote we have to get closer and closer to. But so far, well, that's just 1 point. We need a little bit more before we get a decent plot going. Any questions at all, folks, before we start putting down some more plot points? Okay, we usually don't want to take too much time doing this because, again, our goal is not to make the most perfect graphic ever. If we wanted a perfect sketch of the graph, we'd use technology. The whole idea of this stuff is if you see a rational function, just know what the pertinent information is about it and be able to produce a qualitative, good enough kind of sketch. If we could do that, we're in great shape for quizzes, exams, and the final exam as well. So here's what I would do next to find just a couple more points. Let's calculate f at, not 0, but rather, how about at 1? That might be a good place to start. I just want to know what happens to the function to the right of x equals 1/9. We'll never cross that asymptote, so doing a value to the right of it and to the left of it is probably a good call. F at 1 is plugging 1 right here. We'll get -9 divided by 18 minus 2. And we plug 1 in for that x. So this is -9/16. Let's see, -9/16. That's just about -1/2, but not quite. So when we plug in a 1, if I think of this as a value -1, we'd be probably, let me move that 1 here, right around this location. So, you know what? That's enough information for us to throw down the curve to the right of x equals 1/9, that vertical asymptote. It's below the x-axis. There were no x-intercepts, so now it can't even cross it. Y equals 0 is a horizontal asymptote, so my curve has to get closer and closer to it as we go off to the right. From here, if we go to the left, well, we'll never go through the barrier, but we have to keep on getting closer to it. So it plots in this way. I'll just put an arrowhead once it gets sufficiently close, and that's half the plot. Half the plot is right over here. Now, for the rest of the plot, I don't necessarily know if I should have a value up here or values going like that, unless I do a really fast test point. So let's do this once more. I want a value to the left of x equals 1/9. X equals 0, you know what? That actually does work. I forget we plotted a y-intercept. Our curve is now above the x-axis. It'll never drop down below. So right from here, we can go and make the curve come down. Approach the horizontal asymptote going to the left. And right up here, it's already approaching the vertical asymptote. I'll just draw a little bit extra with the arrowhead to say it's going upwards in that direction. So there it is, folks. That's our function. Y equals f of x. Comes in 2 pieces because we broke the domain and right at 1/9. But that's okay. Both pieces are essentially that one single function. Any questions at all, folks, on producing that plot there? Okay, lots of things we're getting into. But I would say the trickiest part about this is definitely horizontal asymptote. I would always use the cheat sheet theorem that was right up above with the 3 different cases to analyze this. And now for our example number 2, we're going to go through all 3 cases. So let's see what's coming up next. Let's see, we've got 320. I think we have time to do at least 1 more, maybe 2 more. We'll see where we end up. And here's our new function. Let me just copy down the instructions as well, so we're aware of what they were. So for this brand new function here, let's start it in the same order. Oh, good call on that. We can factor the denominator as a difference of squares. Numerator ought to factor as well on this thing. And what would you all say for what the horizontal asymptote should be? Or maybe a better way to think about it is this a numerator wins, or is it a tie, or does the denominator win on this one for degree? This one's a tie. Good call, folks. From the numerator, right here, we have, let me target that arrow better, degree 2. From the denominator, don't forget the negative sign is also important. We have degree 2. And so this one is the tie. To get the horizontal asymptote in this situation, we go like this. Y equals, take the coefficient from the leading term in the numerator, that's a coefficient 4. It stays up above. That's nice, right? To the leading coefficient from the numerator stays in our numerator. That helps us organize this. The leading coefficient in the denominator is not positive 1. It's associated to x squared. And so it would be that negative 1 that's hiding out there. It's just displayed as a sign negative, but it's truly negative 1 times x squared. So we bring this in, it simplifies, and we'll say for horizontal asymptote, I'll just put in a comma and write y equals negative 4. We put these in boxes as well, since these kind of problems are kind of long, work sort of ends up all over the place. I'm going to try to put down the process exactly the same way for all of these. Well, any questions, folks, to that stage? Okay, now for vertical asymptotes, I think it's a good idea to do what you were saying, Michael. This denominator, it ought to factor, and the numerator should factor as well. So let's take g of x. Let's do a little bit of algebraic surgery on it and correct the numerator and denominator. Factored form is just a little bit nicer for these kinds of problems. So down below, it's 1 plus x, 1 minus x as a difference of squares, like you mentioned. So already that's revealing 2 vertical asymptotes because we have 2 ways to have a domain issue down below. The numerator is also important. Let's try to factor this thing. 4x squared minus 8x minus 3. Let me just copy it here. I'm going to delete the right-hand side after we get through it. Think of this for the moment as scratch. And the result of it is going to end up right here. So to factor 4x squared minus 8x plus 3, well, we'll try the trial and error strategy. And first thing to observe is 4 is a perfect square. Sometimes that's good information. Let's try splitting 4 as a 2 by 2. There's no guarantee this works, but usually that's where I would try. If I had like a 25x squared, I'd probably try 5x, for example. So let's go x and x. Positive here says both signs are the same. Negative here says they're not just the same, they're both negative. And primes are always a good call, or a good deal. With a prime, I'm just going to try a 3 and a 1. Here's the check. Oop, I missed. Let me try once more. The check is always the outer product. That's a negative 2x. The inner product, that's a negative 6x. And these have to add up to negative 8x. I think we've got it. So that does the entire factorization for us. Now, actually, let's see if we can leave that there, since sometimes scratch work of how we factored it is just as important of the factorization as well. So with that scratch work, we're claiming that the numerator factors as 2x minus 3 times 2x minus 1. And now we're ready to get vertical asymptotes. Really, we just needed the denominator factored, but we might as well factor the whole thing because that's still good information for us. We'll see later on. For vertical asymptotes, we can just say it right now. There'll be 2 equations. Anyone see what values we should put down for both of those equations? Exactly. From 1, the problem is right here. You can't put a 1 in that location. You divide by 0. Likewise, you can't put a negative 1 there. You have 0 in the denominator for the same reason. Whole thing is undefined, meaning they're not domain elements, meaning they're altogether vertical asymptotes on our graph. So now that we have all that, asymptotes and all, we can start plotting the function itself. Well, at least the asymptotes. We'll combine it with information of the x and y intercepts and a couple more points as needed. So here's my sketch so far. It's our sketch. We're sharing the work here. Now let's start with horizontal asymptote. This one is at -4. Let's go down 4 units. And just a horizontal line. Y equals -4. So this is a guideline. The graph can cross it, but on the very far left, the very far right, our curve must be getting very, very close to it. Next, we'll plot these two. We have +1 here, -1 here. I did change my scale. Going this way, I have a wider scale. And going vertically, it's a little bit more compressed. That's always appropriate if you decide it's just going to look better when you plot it that way. So here's first vertical asymptote. The vertical ones are literal barriers. Your curve can never cross it. And let's actually expand on that just a bit. A good question is, oh, let me fix this as well. This is -1 on this one. A good question folks ask occasionally is, why can't our function cross a vertical asymptote? Yet it doesn't care about a horizontal one. It can and sometimes will cross it. Here's the reason why. I'm going to delete this in a moment. So please don't put this on your page, especially if you're writing in pen. Let's pretend that we had a function that did go like this. It's coming up to the vertical asymptote, and then it crosses it. This is why a function could never actually do that. One thing an asymptote of any kind will do is it still attracts the function. No matter what's happening out here, the function has to return back to that vertical line. But the moment it does that, we have a different kind of problem. This is no longer the graph of a function. Anyone see what the problem is with this black line? It fails the something test. It would be the vertical line test. Yeah, this one fails the vertical line test. In fact, x equals -1 could be that vertical line. It would say, or no, actually it wouldn't be. Let's put this line here. That's the better line. I've intersected once here, twice here. So it's no longer even the graph of a function. So that's the issue with those vertical asymptotes. Horizontal asymptotes does not have the same problem. You could have a function that does say something like this. It could come in, drop down, come up, around, and just eventually settle down to a height at -4. So functions could potentially do that. But there's just less freedom with a vertical asymptote. You know, that's good information for us because it will make plotting much easier, knowing that there's really 3 plots. There's one plot we'll put here. There's another plot we'll put here. And there's a third plot we'll put here. There's 2 vertical asymptotes. We've made 2 cuts. There's 3 regions now. So we need to know what the function looks like on all 3. Let's hide part C. I took some of my asymptotes with it. We can fix that, I'm sure. Well, before we go and put down x, y intercepts and a couple more test points, any questions at all, folks, so far? Okay, so now we're on to this step. Find x and y intercepts. We already have equations of asymptotes in the boxes. And so now for the asymptotes, or excuse me, intercepts, I'm going to use this function right here potentially for some of this work. Let's organize as before. So I'll do x-intercept first. To get our x-intercepts, we're just taking the whole function g of x, setting it equal to 0. But here's a reminder, the only thing that matters in that is the numerator. So you're really setting 2x minus 3 equal to 0, or 2x minus 1 equal to 0. If you set the numerator equal to 0, because we did factor it, that just means either the first factor or the second factor is 0. Really and truly, you didn't necessarily have to put down this work. I mean, it's good to show steps in case we made a simple mistake or partial credit, but you can read off the x-intercepts right from the factored form. Here's how it would go. At the 2x minus 3, just add 3, divide by 2. At the 2x minus 1, add 1, divide by 2. And those are automatically the intercepts we'll be using. If you like ordered pairs, they go like this: 3/2, 0, and 1/2, 0. I'll box this as the official answer, but you could have used these values too, like we mentioned earlier. So we have x-intercepts. We might as well put them on the plot right away. So this is at +1. Or excuse me, that's at -1. Over here to the right is at +1. Our first one is at 1/2. So we'll have a point right here on the x-axis. This one's at 3/2. So that's going to be at 1.5. So there's another point right here. Well, we've got 2 points, folks. That truly helps out. Next, let's do our y-intercepts. So for y-intercepts, I usually start off by writing one single point like this because there can only be one y-intercept if there is any at all. And it's a reminder that you're plugging 0 into the function. So it goes g of 0. All the x's become 0. So on that first factor, we'll have a -3. Second factor here, it's just a -1 when those x's produce 0. But down below, it's just going to be a +1 times a -1. That's 3 negative signs. Whole thing must be negative then. So we get a -3. That's then our y-intercept, right down at -3 in this location here. So we're just about ready to complete the graph. We'll just need a couple more test points to figure out where everything is. But you know what? We can do graph number 2 right now. The way to do this one is we have to use information that the curve is attracted to the asymptote. So on my first attempt here, I'm going to do it wrong, and we'll see why it must be wrong. If I thought it came down like this, I could try to make it come around like there, but I've missed something. I put an intercept right there for the x-intercept when it should have been right there. So that's just the wrong sketch then. I can't fix it by doing this. Or can I? Potentially, that could be the fix for us right here. Yeah, go ahead.
And you get the -1 on the d0 equals -3 times.
Oh, gotcha. This -1 right here.
The one on top.
Oh, for that one. Oh, good call. If I put a 0 there, that ought to have been a +1. I think I just screwed up on that. Thanks for spotting that, Zarek. So right here on my -1, that'd have been a -1 if this was, say, a quiz problem. But then if you did it right over here, I wouldn't take off further credit. Well, let's see if we can fix this here. I intercept at -3. Oh, geez, that's going to be a tough one, isn't it? There we go. Our intercept at -3 needs to change, because this value ought to have been a +1. I think I just saw that negative sign and decided I wanted to include it. But no, if x is 0, that's a +1 here and a +1 here. So this is really +3, which will change the graph on this thing. It goes up to that location there. Does that make sense to folks on that correction? Awesome. This one right here?
The bottom one.
This one right here.
Yeah.
I went 1 plus x. Where did that even come from? Oh, it came from the factorization. 1 plus x, 1 minus x. But we plugged a 0 right here. So we should have got just that +1.
Correct.
Yeah. Thanks for double checking though. For me, sometimes if there's one mistake found, I'm suspicious about the whole thing. If I make one mistake, there's probably more. So thanks for taking another look at it. Other questions so far? Okay, I think we're ready for the punchline then. Well, sort of. I can do the plot on 2. This one ought to go about like this. It comes down, goes through the y-intercept, through the x-intercept, and then approaches the vertical asymptote in that way. So this one's done. I'll delete this information on the top in a minute. It's really just to kind of organize which section we have to work on. We might as do section 1 next. On section 1, well, the curve could go like this following the red dot, maybe, or it could go like this following the red dot. But it can't actually go this way any longer. I'm going to delete this section of the curve in a moment, because if it did actually do this, That would be another x-intercept, but we didn't find any x-intercepts that were negative. So that graph is impossible. So for the rest of it, I'll plot it going like this. Goes down that way and to the left that way. So that takes care of region 1. We really don't even need a test point for this thing. It's just forbidden to have x-intercept. So that gives us really good information on how to plot this one. Well, any questions so far, folks, with those? Okay. Likewise, when we go to region number 3, we know it has to go through here, but there could be 2 options. It might come through, say, like this, for an example, and then just come right back down to the y-intercept. Or it could come through like this and approach the y-intercept in that kind of way. Well, we can't put a 1 inside there. That's a vertical asymptote. We already know what happens at 1.5. How about maybe test out what happens at 2? If we take a look at g at 2, that'll give us some reasonable information to decide what does the curve really look like there. So this will probably be the only test point we need on this one. For g at 2, let me try to do this one a little bit more carefully. I'm plugging 2 right by this red dot. So that'd be a 4 minus 3 for a positive 1 here. 2 goes into this location, so it's 2 by 2, so 4 minus 1. We'll get a 3 right here. Let me scroll just a touch. Plug 2 in that spot, and we'll have a positive 3. 2 here, this would probably be the one that messes me up if I try to just run through it too carefully. This is 1 minus 2, so that one will turn into a negative 1 altogether. Does that look all right to folks with the 2 plugged in? Okay, then let's crank this out. This is altogether 3 divided by negative 3, and we get a value of negative 1. So when we plug 2 into the function, let me move that 2 up here, we get a value of negative 1, so the curve looks like it's going there. At this stage, I'd say we have enough visual evidence to conclude graph should look like this. Comes through, approaches y equals negative 4 to the right, approaches the vertical asymptote x equals positive 1 coming in from the left. So finally, that's our entire curve here. Came in 3 different segments. But really, if this is the function we started with, this g of x function, it's pretty fast to stitch all this together. You can put in a negative 1 or a positive 1. So that's these asymptotes here and here. There's a tie in the degree. So we should be able to take what's effectively a 2x squared, if we were to FOIL this all out, divide by, well, if we FOIL all this out, the leading term below would be a negative x squared. So we should be getting, oh, that's a 4x squared rather. We should be getting a value of negative 4 when we take a look at those coefficients. So there's our horizontal asymptote. Then after looking at x-intercepts, y-intercepts, and an extra test point, just to be sure, that's the plot that we produced. And what I would probably do immediately, if this was an ALEKS problem or a quiz problem, where we're still just practicing this, we should check this out and see if that's even correct and how correct. So let's put this in a plot just for our own visualization to see how we did. We lose the ability to do this if it's a real exam question, so it's good to take advantage of this tool while we can. So I'm going to put in, well, the original function's a good call here because I could have just made a mistake factoring, right? And I wouldn't want that reflected. So we can put in our function as g of x is equal to 4x squared minus 8x plus 3, 1 minus x squared. And here's the plot that we would get. Looks like it has the same basic features as our graph. We try to put in more information like a horizontal asymptote. Then it looks like it's approaching the asymptote correctly as well on all this. So for me, after double checking this kind of graph, I'd say it's kind of shoddy, but that does the job. I would call that an okay sketch. Again, we're not trying to do perfection. We're just trying to get an equation like that and know what is the interesting information about that function on a plot. Any questions at all, folks, on finishing off this one? Okay, well, we've got well, not 5 minutes anymore. There's 4 minutes and some change left over. How about we come back to this one next class, called kind of a mini review to warm us up, and then we'll finish the rest of the problems. Does that sound all right to folks? Okay, that way we don't have to try to do a problem in 4 minutes and some change. That's a bit nasty for these kinds of problems. I would say coming back next class, I'm going to make another document, which is this theorem. I'm going to make it in more of a better printable format so that if you just want something without scribbles on it, that's a highly effective theorem, you'll have a printable file for it. I'm going to put it probably on early Wednesday, right over here, just under 5.6. So there'll be that extra note. Well, have a great night, folks, and I'll see you all on Thursday's class. Thanks.